Okay, so what we have here is a super classic kinematics equation. Guaranteed you'll see this on a test, on a quiz. It gets all the boxes. You're getting scalars, you're getting vectors. So let's dive right in. So we have a bird flies east 22 meters for 2.5 seconds, and then it flies north 10 meters for 1.5 seconds. And then we want to find the distance, the average speed, the displacement, the average velocity. Kind of different for each, but kind of similar. So first thing that's super important is we're given these distances with a direction, right? So not really a distance, but if we want to write down what we have here, I call this kind of the pre-work. Since we have a magnitude, right, of 22 and 10 and a direction of east and north, that means we're given these as vectors, right? So we're given these position vectors. And we can call those delta D1 with a little vector, and we know that's going to be 22 meters east. And we know we're going to have delta D2, which is 10 meters north. All right. And these are vectors, right? So that's important to distinguish because we can also write these down as just straight up scalars. Delta D1, delta D2, 10 meters. And these are our scalars, right? We also have delta T1, which is 2.5 seconds, and delta T2, which is 1.5 seconds. And those, I mean, of course, but I'll write them here, are scalars. Because time, always a scalar, only has a magnitude. You can't have 2.5 seconds east. I mean, it doesn't make any sense. So if we're going through A, B, C, D. So part A says, what is the total distance? So very important, distance versus displacement. Distance is the amount of ground you traveled, right? So if you take, your phone or something or your Apple Watch on you and you walk 22 meters and then you walk 10 meters, your Apple Watch is going to say, well, you walked the 22 meters and you walked the 10 meters. So you just add those together, right? And so distance is a scalar and it just wants to know how far did you go. So we can call this distance, the total distance is just equal to delta D1 plus delta D2. And that's going to be equal to 22 meters plus 10 meters. And we don't care about the direction because distance is just scalar. It's just purely how far did you go. Don't care about distance. And that's going to give us 32 meters. So we can write that the total distance is equal to 32 meters. And that's the answer for part A. Not bad, not bad, right? Distance, if you see distance on a question like this, you just want to know how far you went. So now we have calculate the average speed. So we had distance as a scalar, and the difference between speed and velocity is that speed is also a scalar. It says you take the time, you take the distance, and that'll give you speed. Displacement and velocity we'll get into after. But we want to figure out how long this bird was traveling for, right? So we want to figure out the total time. Let's make a capital T there. And we know the total time is going to be equal to the time of the first leg plus the time of the second leg. And that's just going to be 2.5 plus 1.5 seconds. And that is 4.0 seconds, right? So we have this. And we know from basic kinematics that speed is equal to distance over time. And here the average speed is going to be equal to the total distance divided by the total time. And that will be 32 meters divided by 4 seconds. And that will give us 8 meters per second. So we can write, therefore, the average speed is equal to 8 meters per second. And again, scalar, not a vector, just want the magnitude. We're just saying this bird flew 32 meters, took it 4 seconds, so it had an average speed of 8.0 meters per second. Nice. So now let's move to part C. We're going to see something a little different. So I'm going to flip to a new board here. So part C is saying, again, don't need all caps, what is the total displacement? So displacement is different than distance because all displacement cares about is where did you start and where did you finish? And what's the difference in not, distance or displacement. I mean, that's what it is. How much land, land did you displace in that walk? So what I always want to do for displacement is I want to graph it so I can get a better idea of what's happening. So remember, we're going east for a little bit. So let's call this north, south, west, and east. So we're going 22 meters east. So first we're going, let's change the color here. So first we're going east. We're going east a little bit. Then we're going north for 10 meters. So we have 22 meters, we have 10 meters. So north is going to be a little less. So we have east and then we have north. And because it's displacement, we care about the direction, right? So this is going to be 22 meters east. And this is going to be our 10 meters north. So that means, again, going with this Apple Watch analogy, if you start over here at the origin, you place a pin, then you walk over here and you place a pin over here, and then you ask what's the difference, how far did you travel? Then from pin to pin, you're going to get the displacement. Whereas if you tracked it, you're going to get the distance, right? So you're going to get what we call a resultant vector going this way. And this is going to be our delta dt with a vector. So that's showing that the total displacement. So switch back to blue here. So how do we solve for this, right? We want to solve this. This kind of becomes more of a trigonometry problem here, right? We're going to have some angle over here. And if you think back to grade 9 or grade 10 math, then you know that you can solve for delta dt by using Pythagoras theorem. So we can just write that delta dt, and we need to be careful here because we're just solving for the magnitude, and then we'll get the angle after. So delta dt here is equal to delta d1 squared plus, and this means just the magnitude of delta d2 squared. So the magnitude of delta dt is equal to the same thing under a square root sign. And we can plug everything in here. So delta d1 is 22 meters squared plus 10 meters squared. That will give us 584 meters squared. And we take the square root of that. So make sure you can do this in your calculator because you got to be able to do that. Gives us about 24.2 meters. Okay, so that's the magnitude of delta dt. And I'll keep another significant figure here just for the calculation. So that's great. That's not our answer because that's just the magnitude of delta dt. It's not, it's just the magnitude. So that's going to be different than the distance because here we're actually taking into account the triangle. But what we need is now we need the angle. So the angle here, if we look at this triangle, we have, this is going to be our opposite side. This is going to be our adjacent side. And if you remember SOHCAHTOA, sine likes opposite hypotenuse, cos is adjacent hypotenuse, and then tan is opposite over adjacent. Tan is going to work really nice for us, right? So here, tan of theta is equal to the opposite over the adjacent, which in our case is I'll write it down here. So tan theta is equal to the magnitude of delta d2 over the magnitude of delta d1. So that means that theta is equal to the inverse tan of, we just plug these in, which will be 10 meters over 22 meters. And we get an angle of, very similar, 24 degrees. So these numbers just happen to work out nicely. We get 24, we get 24. And then we can write that the total displacement with the vector is equal to 24 meters. And then the direction is important because we have our angle coming from the east and going north. So it's starting east, then going north. So the way we write that, if it's starting east, we write east, and then the angle 24 degrees, and then we're going north. So east 24 degrees north. That is a bad 4. I'll make it a bit better. East 24 degrees north. And that is our total displacement. Not too bad. Just got to know Pythagoras, got to know some tans, your cosines. And if we go back, we still have to calculate the average velocity of the bird. So we know that the total displacement, did I spell that right? I think so. Total displacement is delta dt equals 24 meters, and then east 24 degrees north. So for average speed, it was just distance divided by time. So big surprise. Average velocity is going to be total displacement divided by time. And this works because you're just dividing a vector by a scalar, and that's just reshaping the magnitude. It's not going to change the direction, right? So we have 24 meters east, 24 degrees north, divided by the total time was 4 seconds. And that will give us an average speed of 6 meters per second east, 24 degrees north. So therefore, I like to do a therefore, pretend you're on a test. 6 meters per second east, 24 degrees north. And there we go. In this one question, you've conquered distance, displacement, speed, velocity. You've done it all. You've used Pythagoras, you've used vector addition, you've used your ideas of what scalars and vectors are and the differences, and not too bad. But let's see what happens when the motion isn't just in straight lines, but you get them at angles from each other. That's going to be interesting.